Yeah, welcome. So in the last lecture, we have discussed about entailment. In this lecture, we'll be starting with inference procedures or inference algorithm, and we'll be discussing an introduction to propositional logic. Okay. So 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 we have discussed entailment, which is represented something like this. So if it is represented like this, it means that the knowledge base KB, it entails the statement alpha. Okay. So now we are going to discuss about inference procedure or inference algorithm. Say there is an inference procedure I which can derive a sentence alpha from the knowledge base KB. There is an inference algorithm I which can derive the sentence alpha from the knowledge base KB. And that is represented something like this KB, this symbol I alpha. So when something is represented like this, it means that there is an inference algorithm I which has derived and sentence alpha from the knowledge base. Okay, fine. Now we are going to discuss about the properties of this inference algorithm or the inference procedure. So this inference procedure uh, is supposed to have or uh, the the efficiency of this inference procedure or this algorithm is measured by these three parameters. One is soundness, the other one is completeness, and the other one is grounding. Based on these three parameters, we can identify like how good this inference algorithm is. So the first property is soundness. What is soundness? Soundness uh, means, so don't read this, just try to understand. Soundness means whatever this inference algorithm derives, whatever the sentence this inference algorithm derives, all those sentences are true. In that case, the algorithm will be called a sound. Is that okay? So, so, so when we say something like this KB, this symbol I alpha, it means there is an inference algorithm I which derives alpha from the knowledge base KB. And when will we say that this inference algorithm is sound? This inference algorithm is sound if whatever the sentences it derives, if whatever the sentences that it derives from the KB, and if all those sentences were correct, then correct in the sense if it is true, then we'll call that inference algorithm as sound. Okay. So what is the catch here in the sense? The catch is whatever it derives, they are correct or they are true. That doesn't mean that it derives all the sentences. So actually say the total number of sentences, the total number of sentences that can be derived from KB, let us assume it is 100 sentences can be derived as a whole. But assume there is an inference algorithm I. This inference algorithm is able to derive 50 sentences from this KB, right? And whatever the 50 sentences is derived, all are true. They are correct. In that case, we call this inference algorithm as sound. It has not derived all the sentences, but whatever it derives, they are true, right? So this is how soundness is defined. So I is the inference algorithm. The inference algorithm I is sound if whenever this is nothing but whenever there is an inference algorithm I which derives the sentence alpha from the knowledge base KB, uh, is also true that KB entails alpha. KB entails alpha means uh, so, so so KB entails alpha, that you know the meaning, that is wherever KB is true, alpha is true, which means that sentence is true. So it does not make any wrong inferences, but it may not make all inferences. So that is the key thing you should identify, you should understand. It, it will not make any wrong inferences, but it may not make all the inferences. So such an algorithm, if the algorithm holds this property, then we call it as sound. Okay, and when will we say the algorithm is complete? An algorithm will be said to be, the inference algorithm will be said to be complete if it derives all possible sentences from KB. Okay, if it derives all possible sentences from KB. So, so say that from KB, totally we can derive 100 sentences. Now say there is another inference algorithm J. This inference algorithm, say it is able to derive, this algorithm J, it is able to derive 120 sentences from KB. But say maximum it's only 100 sentences, but it is able to derive 120 sentences. Out of these 120 sentences, say these first 100 sentences are true. That is, they match the KB. The remaining 20 sentences are not true, but still we call J as complete. Why we are calling it as complete? Because it is able to derive all the sentences from KB. Okay. So completeness is the inference algorithm I is complete if whenever KB entails alpha is also true, that that the inference algorithm is able to derive the statement alpha from KB. So here we are starting with KB entails alpha, which means for all sentences in KB, for each and every sentence in KB, we have this inference algorithm which can derive alpha from KB. That's the meaning. So the point here is all inferences can be made, but but it may make some wrong inferences also, some extra wrong inferences also. Okay, so this is how we derive, this is how we define the soundness property and completeness property of the inference algorithm. There is another property called grounding. What is meant by grounding? See, grounding is an interesting property because this inference algorithm is just an algorithm. Inference algorithm is just an algorithm, that is, it is in the it is a piece of code that is written in the agent. But this inference algorithm should replicate, or it should reflect whatever is happening in the real world. There is something happening in the real world, and this inference algorithm should behave in sync to the real world. So that means for example, if we say that by using for example, if we say that uh, the inference algorithm is deriving something from something, so the inference algorithm is deriving a b from a. Okay, then in the real world also is the same thing is happening or not? That checking that is called as grounding. So say the inference algorithm may derive b from a by following all the syntax, all the rules of the language or the grammar perfectly, and then it may derive. There may not be anything wrong syntactically how it derives a particular sentence from something else, from the knowledge base or whatever it may be. That is fine. So with respect to its syntactic part, it is fine. But whatever it derives, whatever it derives, is it in accordance with the real world? In the real world also, will it will it happen in the same way? If it happens in the same way, then the algorithm is said to be grounded. Otherwise, the algorithm will not be grounded. Okay. So so this is how we define grounding. Uh, so here is an interesting diagram. This says what is grounding. See, this is this bottom part of these dotted lines. It represents the real world. What is happening in the real world? In the real world, if something aspects of the world, if this say this is one state, this is state one. From this state, if some event happens, then the real world will become something like this. Okay. Now, if you have a rule in the representation, so inference algorithm is nothing but some way of representation. So in the agent you are representing something. So in the agent also, if you should have a rule something like this: s1, from s1 you can go to s2, right? Or exactly what we are trying to say in the sense, when there is a rule in the representation something like this, is the same thing also happening in the real world, right? So in the representation you say that s1 entails s2, but in the real world also, is it reflecting or not? If it reflects, then we say it is grounding. If it does not reflect, then it is not grounding, right? So I'll tell you one simple example. Say in the real world, you are purchasing first 2 apples. Okay, then you are purchasing 3 oranges. Okay, then it means totally you have something 5 fruits. Okay, 5 fruits. So this is what happens in the real world. But say for example, you are writing an inference algorithm which does a calculation something like this. That is, uh, two object plus 2 objects of one type plus 3 objects of another type will give 6 objects totally. Like that, you are writing an inference algorithm. Okay. So now syntactically you are proving that this is correct. Mathematically it is not correct, but syntactically somehow you are proving that it is correct, and your software is not giving any error. Are you getting? Your software is not giving any error. There is no error at all. You are able to compile this program, and you are able to implement this logic in the agent. Now the agent will behave like this. That is, whenever it encounters 2 object and 3 object, it will add it to 6 instead of 5. So in that case, this is not grounded. So this is an example of ungrounded, or it is not being grounded, because how the logic behaves, or how the agent behaves, or how the inference algorithm behaves, it is not reflecting the behavior of the real world. Okay, so this is what exactly is grounding is. So grounding is very much similar to in programming languages. There are 2 types of error, right? One is compile time error. Compile time error and the other one is runtime error. So compile time error happens what, or it's not even runtime error, logical error. The second thing is logical error. See, what is compile time error? Compile time error happens because of your something wrong you have made syntactically, right? So that is at a top level mistake. So unless you solve the you make it syntactically correct, you cannot execute the program. So compile time error is nothing but a syntax error. But what is logical error? There is no syntax error, but syntactically it is correct. But in the logic, in the actual way of getting things done, there you have made a mistake. So now your program may behave, your program may execute, but it may not execute in the way in which intended. Right? So that is what grounding is about. So your inference algorithm may may follow the syntactic rule and it may behave perfectly, but is it reflecting the real environment or not? If it is reflecting, then the algorithm is said to be grounded. Otherwise, it is not grounded. Right? So the connection between logical reasoning and the real environment in which the agent exists. So that is called as grounding. Okay. So based on these 3 features or properties, the efficiency of an inference algorithm is measured. Right. I guess you have understood. Okay. So so now there is a question. Now you have understood probably what is grounding. Now there is a question. How do we know that the knowledge base is true in the real world? That is, how do we know that KB is grounded? KB. So whatever. So KB contains what set of sentences. So KB may contain 10 sentence or 100 sentence or even 1,000 sentence. So it contains n sentences. Now, if KB, when can we say KB is grounded? If all of these sentences are 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 reflecting in the real world. If all of these sentences are connected to the real world, then we can say that KB is grounded. Now there is a question: how do we ensure that KB is true in the real world? So how do we ensure? In the sense, we ensure that KB is true through the agent's sensors. So agent's sensor is the one which creates connection with the real world, and through that we are quite sure that whatever the statement that is added in KB, that is in synchronization with the real world. Okay. For example, let us take an example of this Umpus world. Say the Umpus world agent is it has a smell sensor. It has a smell sensor. Okay. And if it senses some smell, if it senses some smell, then what it will do? Then it will add a suitable sentence into the knowledge base. Okay. assume that currently umpus is in the cell 1 comma 2, right? So assume currently umpus is in the cell 1 comma 2. So if it is in the one, if it is in the cell 1 comma 2, it will it will it could sense stench, right? So when it senses stench, then what it understood, that there is umpus, where umpus should be, either in 1 comma 1, because there is stench in 1 comma 2. So it should be either in 1 comma 1 or it should be in 2 comma 2, right? Or it should be in 1 comma 3. So umpus should be in any one of these three cells. As the agent is coming from 1 comma 1 to 1 comma 2, so probably the agent can rule out this. Apart from this, the agent knows that umpus is in either 2 comma 2 or in 1 comma 3, right? Or even if it uses more inference, say previously at first the agent will move from 1 comma 1 to 2 comma 1. When it goes to 2 comma 1, it has experienced only breeze, there is no stench, which means that there is no umpus in 2 comma 2, because if umpus is in 2 comma 2, here also the agent should have experienced stench, but it has not experienced. So with that, the agent knows that umpus is not in 2 comma 2. Now the agent can confirm what? Agent can confirm that umpus is in 1 comma 3. So this is grounded, right? So based on sensing and based on inference, this is a sound knowledge, or it's a very perfect knowledge. And it is not just a rule, it is a fact in the real world also. So whatever the rule we are adding, if that is truly connected with the real world, then we call it as grounding. So this is one typical example of grounding. So now we know that umpus is in 1 comma 3. So now the agent will add a rule. What rule it will add? Umpus is in 1 comma 3. Like that, it will add a rule. Confidently, it will add, and that rule is correct. So this is how we ensure grounding. Okay. So then whenever the sentence is in the knowledge base, it is true in the real world. So when you do such inferences and when you add, whatever the sentence you add, it will be also true in the real world. Okay. So 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 the belief that umpus causes smells in the adjacent squares. So 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 this is already we know that wherever umpus will create what you call the stench in the adjacent cell. So based on this particular rule is added and grounding is ensured. But there is another question. How does the umpus know? So this is basically a question. How does the umpus know that? Sorry, how does the agent knows? How does the agent knows that the presence of umpus will create smell in adjacent square? So probably you may ask, so how the agent know? So initially, how the agent know that if there is smell, then in the nearby room there is umpus? How it knows? So that is known through learning, nothing else. That is known only through learning. Probably once or twice the agent might have killed by umpus, and whenever the agent is getting killed, he might have experienced smell in the adjacent cell, and based on that, the program might be learning, or this basic informations can be fed by the programmer. Okay, fine. Now let us discuss a brief introduction to propositional logic, and also we'll try to understand like how this umpus world problem can be represented using propositional logic. Okay. So the propositional logic is the most simplest form of logic. So they are basically used to represent facts, right? So for example, here uh, we use P1, P2, such propositional symbols to represent sentences, right? So it need not be P1, P2, it can be S1, S2, some variable we use to represent a sentence, right? And that sentence we call it as a proposition. Okay. For example, we say that, see, there is a sentence, sun rises in the east. Okay. So now whenever we want to use this sentence, we say that just P1. So P1 means sun rises in the east. Okay. So like that. So like that every sentence. So and for so this is a sentence. This sentence can be associated with the truth value. It can be either true or false. In this case, it can be true. It is true. Instead of that, if I say the sun rises in the west, then this is also a sentence, and this is also a proposition, but its truth value is false. Okay. And on propositions, so on each of the proposition, so proposition is basically a sentence. On each of this sentence, we can perform some operation. So the simplest form of operation is negation. If S is a sentence, then negation of S is also a sentence, right? So that is, if sun rises in east, if that is a sentence, then sun does not rise in the east. That is also a sentence. Okay, we are not talking about the truth of that sentence. So that is the truth value may be either true or false. Okay, if S1 and S2 are sentences, then S1 and S2 is also a sentence. So this is something like a compound sentence. S1 is one separate sentence, S2 is another separate sentence. Then you can combine S1 and S2, and that is also a sentence. So this operator is called as conjunction. As per propositional logic terminology, it is called as conjunction. This and symbol is called as conjunction. Okay. Say for example, there is a sentence S1 which says that uh, Ramu lives in Hyderabad. Ramu lives in Hyderabad. This is one sentence. So there is another sentence which says that Ramu is studying BTech. Okay. Then this two sentence, then S1 and S2 is also a sentence. That is Ramu lives in Hyderabad and Ramu is studying BTech. This is a sentence. If S1 is a sentence, if S1 and S2 are sentence, then S1 or S2 is also a sentence. So that is called as disjunction. Okay. So right. So so in this case, or is not meaningful, but still we can apply or. So let us not think about the logic, but wherever meaningful, you can have or, right? Okay. So uh, so basically, if there are two sentences, then they can be connected by using or. Okay. So for example, uh, say the sentence S1 is say okay, say there are two sentences. Sentence S1 says that Ravi used to do exercise daily morning. Sentence 1 says that Ravi used to do exercise daily morning. Sentence 2 says that Ravi goes to temple every morning. So now these two can be connected using or. So Ravi used to do exercise daily morning, or Ravi goes to temple every morning. So basically, if you have two different sentences, then they can be connected using or. Okay. And there is another so these are something like connectors. Even this also, and or, all these are connectors. So if S1 and S2 are sentences, then this is called as implication. Then S1 implies S2 is also a sentence. Okay, what is implication we will learn. So just now understand that S1 implies S2 is also a sentence. Then if S1 and S2 are sentences, then this is also a sentence. This is called as bidirectional. So this is called as bidirection. So S1 implies S2 in the sense it says that if S1 is true, then S2 is true. That's all. It only tells us this information, nothing else. If S1 is true, then S2 is true. That's all it says. Okay. So whenever S1 is true, S2 will be true. It confirms that. It guarantees that. Are you getting? But it does not says. But it does not says anything about what about S1 is false. Okay. So it only says if S1 is true, then S2 is also true. We'll discuss that in detail later. But as of now, you understand this much. But when you see bidirectional, S1 bidirectional S2, it means that, so this is basically two way. S1 implies S2. Bidirectional is S1 implies S2 and S2 implies S1. It is both the way. That is, whenever S1 is true, S2 is true. And whenever S2 is true, S1 is also true. Okay. But this implication, it talks only about S1. If S1 is true, S2 is true. That's all it says. Okay. It is not coming in the reverse direction, but it is taking both the cases. Okay. Fine. So now, how do we represent this Wumpus world problem using propositional logic? Say for example, now we can use this symbol. Say for example, P12. P12 is false, which means that there is no, so here P represents pit. Here P represents pit, which means that there is no pit in the cell 1 comma 2 or in the floor 1 comma 2. Okay, right? Or if you say that P2 comma 2, which means that there is a pit in the cell 2 comma 2. Okay. Or if you say P3 comma 1, which means that there is no pit in the cell 3 comma 1. Whether there is really pit or not, let us not get into that. But this is how we represent information using propositional logic. Okay. Now, fine. Now you know what is, now you know. So in the previous slide we have discussed that if S is a sentence, then not S is also a sentence. So here we are discussing. Uh, Here we are discussing the, what you call, the truth value associated with it, right? So if not S is true, if not S is true, then obviously S will be false. Okay, and the reverse way. If S is true, then not S will be true. And what is S1 and S2? When S1 and S2 will be true? S1 and S2 will be true if and only if and only if S1 is true and S2 is true. So if there are two sentences S1 and another sentence S2, when this S1 and S2 will be true? Only if both of them are true, then only. Okay. S1 or S2 is true if and only if S1 is true or S2 is true. Okay. This implication and bidirectional we will discuss with an example. We will discuss with the truth table. Okay. Now let us see the truth table. So this is a truth table. So this is P and this is Q. So these are the values it can take: false, 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 true, true, false, and true, true. So you know not P, it's straightforward. Not P is reverse of P. This is false, here true. This is false, so here true. This is true, so not P is false. This is true, so not P is false. And what is P and Q? It will be true only when both P and Q are true. So when P and Q are true, the result is true. In all other cases, it is false. And what is P or Q? It will be true when either P or Q is true. So it will be false only when both were false. So at this place it is false. In all other places it is true. Okay. Now what is implication? What is P implies Q? So this is our key to understand. So P implies Q. It says only one thing. Please understand clearly. It says only one thing. It says that if P is true, then Q is true. If P is true, then Q is true. Nothing else it says. Okay. So you just see where P is true and Q is true. So here P is true and Q is true. So the output here is true. Because that is the rule says. The rule says that if P is true, then Q is true. Okay. So here there is, see this. Here there is a situation where P is true, Q is false. So this is something like which is contradicting the implication. Because the rule of the implication, what it says, if P is true, then Q is true. So P true, Q false is not possible. So here the output we are writing false. Okay. Because the rule of the implication is if P is true, then Q should be true. If P true and Q false, that is not acceptable by P implies Q. So it is false. Okay. right? Now what about the other cases? If P is false, then what can be Q? What should be Q? Does the rule says anything? Nothing it says. So the rule of P implies Q says that if P is true, then Q is true. If P is false, it is not telling anything about the Q. Then it means that if P is false, Q can be anything. Q can be either true or false, right? So P is false, Q is false. It's acceptable by implication because it does not. It is not. It does not bother. Okay. It is only more specific that if P is true, then Q should be true. If P is false, Q can be anything. So if P is false and Q is false, yes, it is acceptable by P implication implied Q. So it is also true. If P is false and Q is true, fine, that is also okay. If P is false, Q can be anything. So this is also true. Okay. So this is the truth table for P implies Q. So basically it is false only for this case when P is true and Q is false. Because this is the only case which is not acceptable by P implies Q. Okay. Other cases are acceptable. Now what is bidirectional P bidirectional Q? So basically what does it mean? It means that P implies Q and Q implies P. So what does it mean? It means that if P is true, Q should be true. And also it says that if Q is true, P should be true. So first let us identify these cases where P is true and where Q is true. Here P is true, Q is true. So this is true. Okay, right? And where Q is true, if Q is true, then P should be true. Okay. Here Q is true. Here Q is true, but P is not true. So this is not acceptable by bidirectional. So this is false, right? Okay. And and does it says anything about Q being false? Does it says anything about Q being false? So it only says that if Q is true, P should be true. Does this rule says anything about Q being false? If Q is false, P can be anything. Okay. So if Q is false, P can be anything. P can be see, yes, just a minute. Okay. See see P bidirectional Q, right? See, simply let us understand that P bidirectional Q, this is true only for these two cases. If if P is false and Q is false, it is true. And if P is true and Q is true, then also it is true. Okay. But how it is? See, it is little tricky, but it is not difficult. So what does P bidirectional Q means? It means that P implies Q and Q implies P. Okay. So let us split it out. So what is P implies Q? P implies Q means if P is true, then Q should be true. So which satisfies that? This one satisfies this. So it is and. So both should be happening. If P implies Q and Q implies P. So this is for P implies Q, right? Similarly, what is for Q implies P? If Q is true, then P should be true. So for that also, this is okay, fine. Okay. So this satisfies both. It satisfies P implies Q and Q implies P. Okay, fine. Now what? Now let us see only this rule. If P is not true, then what can be Q? As per implication, it is only talking about if P is true, Q should be true. If P is not true, then Q can be anything. Then if you see only this rule, if you see only this condition, then both these cases should be true. Okay, because it says that P implies Q. So if P is false, Q can be anything. So both of this should be true, right? But we have taken only one condition. But let us take the second condition also. Q implies P. So what does Q implies P means? We have already discussed about for the case of Q is true. Now what is Q is false? If Q is false, P can be anything, right? If Q is false, P can be anything. So this is if Q is false, P can be anything. This first one satisfies that. But this one, if you see here, Q is true. This is Q is true, but P is false. This cannot happen. As per this rule, this cannot happen. So this we cannot include. So this we are making as false. Are you getting? So that is how this is ruled out. But this is acceptable by both P implies Q and Q implies P. Because if you take P as false, then Q can be anything. Similarly, if you take Q as false, P can be anything. Right? Okay. Now similarly you come for Q implies P. So Q implies P, the positive cases we have discussed. For negative cases, if Q is false, then P can be anything. Right? So which are the cases Q is false? One is this and the other one is this. In these two cases, Q is false. So time being, let us understand that for this both the cases we are keeping true. Okay, this is also true. This is also true. Now, what the rule says, if Q is false, P can be anything. So, so this is this satisfies this. This condition is getting satisfied for this rule, and this condition is also getting satisfied for this rule, because here Q false, P is true. Here Q false, P is false. If Q is false, P can be anything. But when you consider this first rule, it says that if P is true, Q should be true, right? So here when you see P is true, but here Q is false. So this again, this cannot be taken. So this will be what? False. So finally, we left out with only these two cases where it is true, right? I guess I have justified. So you think of, so this is how this truth table works, right? Okay, so you should know these things because we'll be using this hereafter at many places. So you should know all these things, right? Okay. Now coming to the Umpus world representation. So now how we are going to use this proportional logic in Umpus world. So let Pij be true if there is a pit in I comma j. So if there is a pit in I comma j, then we say that Pij is true. Similarly, let Bij be true if there is a breeze in I comma j. So if there is breeze in the cell I comma j, then we represent that as Bi comma j, right? So initially the agent is starting at cell 1 comma 1. So in this cell 1 comma 1, there is no pit. So we are saying that not pit 1 comma 1, there is no pit. And the agent is not sensing any breeze. So we say that it is not breeze, right? Similarly, you can add further also. There is no stench also. So no stench at 1 comma 1, so on and so forth. So like that, this is how we represent knowledge using proportional logic. So now in all the cells, what is the status, you know? So everything you can represent like this. Okay. So but after the agent moves to the cell 2 comma 1, here in the cell 2 comma 1, the agent senses breeze. So that is represented as B2 comma 1, because in the cell 2 comma 1 there is B, there is breeze. So this B represents breeze. Okay. Say there is a rule which we want to represent through proportional logic. The rule is pits causes breezes in adjacent square. So this is a general information or a knowledge. This you want to represent to the agent of the Umpus world, this agent. Then actually there is no way to generally represent this. Using proportional logic, we cannot just give this one sentence. Pits causes breezes in adjacent square. Like this, we cannot, in a generic sense, we cannot represent. Actually, for every cell you have to write like this. For every cell you have to write like this. If there is breeze in 1 comma 1, it means that there is pit in 1 comma 2 or 2 comma 1. So like that for every cell you have to write. So if here if there is a breeze, then what does it mean? There is a pit either here or here. Okay. So for that we are using bidirectional. Why we are using bidirectional? Because it is applicable both the ways. If there is breeze here, then it means there is a pit either here or here. If there is a pit either here or here, then obviously there will be breeze in 1, 1. Okay. Similarly, if there is a breeze in 2, 1, it means what? There is a pit either in 1, 1. Here we are not using any inferences. This is just mentioning only this info. Pits causes breezes in adjacent square. Only we are talking about only that focused knowledge. So if there is breeze in 2, 1, it means pit can be either in 1, 1 or one. What else? If there is breeze in yeah, if there is breeze in 2, 1, it can be either in 1, 1 or 2, 2 or 3, 1. Right? Similarly, say if there is breeze in, so these are just rules. Okay, if there is breeze in 3, 1, then what does it mean? Here, if there is breeze, then pit can be either here, here, or here. So which is nothing but pit can be either in 2, 1 or pit can be in, what is this? This is x-axis 3, y-axis 2. So 3, 2 or pit can be in 4, 1. Okay. So like that, we can represent the knowledge. Right? Fine. But you might have now understood representing knowledge like this, it's very complex, because now for every single thing you have to represent the knowledge. For n symbols, the time complexity will be order of 2 to the power n. Okay. So if there are n such symbols, then the time complexity will be 2 to the power n, because for every symbol you have to represent whether it is true or not true. So we need some better way of representing knowledge, because proportional logic is not much expressive. Okay, fine. So now, if two sentences are logically equivalent, what does it mean by logically equivalent? When we say that the two sentences are logically equivalent, we say that two sentences are logically equivalent. So logically equivalent is represented using this symbol if alpha entails beta and beta entails alpha. So you know what is alpha entails beta? So alpha entails beta means wherever alpha is true, beta is also true. And beta entails alpha means wherever beta is true, alpha is also true. So two sentences are logically equivalent if alpha entails beta and beta entails alpha. Right? And there are some other rules of uh, what you call of logics. So probably you might have learned these things somewhere else in discrete mathematics or something like that. So alpha and beta is equivalent to beta and alpha. Alpha or beta is equivalent to beta or alpha. This is the rule of associativity. Alpha and beta and alpha is equivalent to alpha and beta and alpha. Alpha or beta or alpha and beta and gamma is equivalent to alpha and beta and gamma. Alpha or beta or gamma is equivalent to alpha or beta or gamma. Okay, this is associativity of and, this is associativity of or. Negation of negation alpha is equal to alpha. Double negation will eliminate the negation. Okay. So this is interesting. This you should remember. Alpha implies beta. Okay. So these two things you should remember. Alpha implies beta can be alpha implies beta is equivalent to not beta implies not alpha. Okay. So when we say alpha implies beta, it also means that not beta implies not alpha. So this is called as contraposition. Okay. And alpha implies beta can be represented like this. See, this second representation we use in most places. Okay. Alpha implies beta. Alpha implies beta. Instead of writing alpha implies beta, we can also write as not alpha or beta. Okay, we can also, this alpha implies beta can be represented as not alpha or beta. Also be represented as not alpha or beta. Fine. So we'll discuss further about this. And alpha bidirectional beta is nothing but alpha implies beta and beta implies alpha. So this is which we know already. And not alpha and beta can be represented like this: not alpha or not beta. Okay, so when the not goes in, it becomes or. And not alpha or beta can be represented as not alpha and not beta. And this is a distribution of conjunction over disjunction. Alpha and beta or alpha is equivalent to alpha and beta or alpha and gamma. Alpha and beta or gamma is equivalent to alpha and beta or alpha and gamma. Similarly, alpha or beta and gamma is equivalent to alpha or beta and alpha or gamma. Right. Okay. So now let us try to understand what is meant by validity and what is meant by satisfiability. So we say that a sentence is valid if it is true in all models. A sentence is valid if it is true in all models. In a given world, in all the models, if it is true, then we say it is valid, right? For example, A or not A. So if you have something like this, surely it will be true for all the cases. So if A is true, then not A will be false, but true or false is false. True or false is true. Okay. If A is false, then not A will be true. Then also false and true will be true. So this is something. This is an example, but basically your understanding should be like this. If a sentence is true in all the models, then we say that it is a valid sentence. Okay. So validity is connected to inference via deduction theorem. KB entails alpha. KB entails alpha if and only if KB implies alpha is valid. Okay, so this is one example of validity. Through so when we can say that KB entails alpha, we say that KB entails alpha if and only if KB implies alpha. So what does it mean? You may see. So you know what is KB. You know what is implication. So implication will be false only under this case when P is true and Q is false. Only in this case it will be false. In all other cases it will be true. Okay. So what this statement says, KB entails alpha if and only if KB implies alpha is valid. Okay. So it means that wherever KB is true, alpha should be true. So that is what implications talks, right? Wherever KB is true, alpha should be true. If that is satisfied, if that is valid, then we say that KB implies alpha. Okay, then we say that uh, KB. So yeah, so so this is so if KB implies alpha, then we say that KB entails alpha, because KB implies alpha means what? Wherever KB is true, alpha is also true. Then this is also satisfied. So this is one way of explaining entailment through validity. Then what is meant by satisfiable? A sentence is satisfiable if it is true in some model. It need not be true in all the model. A sentence is satisfiable if it is true in some model. So A or B. So if any one of them is true, that is fine. Okay. A sentence is unsatisfiable if it is false in all the models. Okay. For validity, it should be true in all models. But for satisfiable, it is enough if it is true in some model, or at least in one model. And the sentence is unsatisfiable if it is false in all the models. Right? So for example, A and not A, it will be always false. If A is true, not A will be false. So A and not A will be false. If A is false, not A will be true. Then also false and true will be false. Right? So here is one example of satisfiability. Satisfiability is connected to inference via the following. Again, we are taking the same thing. KB entails alpha if and only if KB and not alpha is unsatisfiable. So what does it mean? KB and not alpha. See, KB and not alpha is what? It means KB is true, alpha is false. Okay. KB and not alpha represents what? KB is true, alpha is not false. Alpha is false. This is the third case. This is the third case. Okay. So that is actually not possible. If So when we say that P implies Q, if P is true, then Q should be true. P true, Q false is not possible. That case is false. Okay, so here that is what we are taking here. KB entails alpha if and only if KB and not alpha is unsatisfiable. That is, you are unable to satisfy that. So what does it mean by unsatisfiable? When we say that something is unsatisfiable, what is the unsatisfiable? If it is false in all models, if it is false in all cases. So for all values of KB, okay, if you are able to prove that this is not possible. So basically this is not possible because uh, because there is no model for which KB equal to true and alpha is false, right? There is no model for which KB is true and alpha is false. So that is what it means. uh, Here we can prove satisfiability with this, right? So this is the meaning of this. There is no model for which KB is true and alpha is false. So for example, let us assume KB is true and alpha is false. Then what does it mean? So if KB is true and alpha is false, okay, then it means what? If KB is true and alpha is false, then it means that KB does not entails alpha. Okay, so this should not happen. This should not happen. That's what this condition says. There should not be any case. There should not be even a single case for which KB is true and alpha is false. That should not happen. If KB is true, alpha should be true. So that we say that this should be unsatisfiable. Then we can say that KB entails alpha. So this is just representing this in a different way. Here we are representing KB entails alpha using validity. To use validity, KB entails alpha is represented through validity using this notation. KB implies alpha. KB entails alpha is represented using satisfiability using this notation. Here we cannot use satisfiability, we have to use only unsatisfiability. So we are saying that KB entails alpha if and only if KB and not alpha is unsatisfiable. You should not be able to satisfy this, which means there is no model in which KB is true and alpha is false. Okay, fine. So let us stop here for today's session. Thank you.